folks, checking out class 50. It's the beginning of unit 6. We're talking about momentum and impulse today and introducing them. So we started class by throwing an egg at a bed sheet, and the question is, why doesn't the egg break when thrown at the bed sheet? So just jot down your ideas there. We'll kind of get into it during this class. So we have to define a couple terms, momentum and impulse. And momentum you've probably heard of before, impulse maybe not. So actually going to talk about momentum first. It's the one down here. I should probably change the order of these two. So momentum is the product of an object's mass and the object's velocity. Okay, so momentum, which we abbreviate with a capital letter or a lowercase letter p, is equal to mass times velocity. Okay, we abbreviate with a lowercase p. It is a vector, so it can be either positive or negative. And let's know what the units for momentum. Well, we have mass, which is kilograms, and we have velocity, which is meters per second. Kilograms times meters per second. Now let's just take a moment to go talk about impulse for a second. So impulse, by the way, this equation is on the reference table down here, so you don't need to memorize it. Impulse is the product of the average force acting on an object and the time interval over which it acts. It is abbreviated with a capital letter J. So on your reference table, the equation looks something like this. J equals F net times T, which we'll frequently just write F times T, which is also equal to delta P. Now, a few things. A lot of people don't realize that each one of these terms is equal to any other term, meaning I could write this as J equals F times T. I could write this as J equals delta P. Even though they're not right next to each other, they are equal. And I could also say that F times T equals delta P. An important thing to note is that delta P is P final minus P initial. Anytime you see delta, it's always final minus initial. Now, the units for impulse, a couple different things you could do. You could say that they are newtons times seconds, or you could say that they are kilograms times meters per second because they're also equal to the change in momentum. So the units for momentum and impulse are actually the same. And we'll actually find that momentum and impulse are really just two sides of the same coin. So really quickly, let's calculate momentum just to practice. So P equals mv. So P equals 64 kilograms, 5.6 meters per second. Throw it in my calculator real quick. And I get 358.4 kilograms times meters per second. All right, now let's find the impulse here. So impulse, we're going to use, let's see, we could do change in momentum or force times time. I think force times time is easier here. So J, oops, J equals force times time. It's equal to 5 newtons times 3.4 seconds. And let's see, that comes out to be, I think, 17 newtons times seconds, or kilograms times meters per second. All right, now let's look at the next bit here. How can a force versus time graph be used to find the impulse acting on an object? Just justify your response by mentioning the units. So what I'll mention here, so this is milliseconds, which can be confusing. It's the area, okay? Because you could look at it, well, area is base times height. Your base unit is seconds. Your height unit is newtons. Newtons times seconds. So we define the area to find that here. So area equals 1/2 base times height. We have 1/2. The base is going to be 40 seconds. And the height here is about 100 newtons. So this comes out to be 2,000 newtons times seconds, or again, 2,000 kilograms times meters per second. Those are interchangeable. So this brings us to the impulse momentum theorem, this idea that a force acting on an object for a certain period of time changes its momentum. So this basically says if a net force acts on an object, its momentum changes. And if an object's momentum changes, a net force must be acting on it. And I'm saying net force because there can be situations where two forces are acting on an object and they're equal and they're opposite directions, so they cancel each other out. So there is no net force. So net force again is like the total force added up. Okay. So I'll look right here real quick. So one thing I want to make note of um, is that this impulse momentum theorem is actually something we've seen before. If we start with force times time equals delta p, I can write force times time equals mv final, that's final momentum, minus mv initial, that's initial momentum. Then what I can do is I can just group and take out an m out of both terms. So I have m times, in parentheses, v final minus v initial, replace that with delta v, and divide both sides by t, and I can get force equals m times delta v over t. Delta v over t, change in velocity over time, is acceleration. You actually just get F equals ma. So this is actually just F equals ma rearranged. Sounds strange, but that's all it is. It's just F equals ma rearranged. Okay, we'll find that it helps us solve some questions a little bit more quickly than F equals ma could. So let's go back to the egg demonstration. The egg has a mass of 0.1 kilograms, and let's say I threw it at 15 meters per second. That's about 33 miles an hour. And whether the egg hits a wall or a bed sheet, its final velocity is zero. It stops, right? So let's think about if the egg were thrown at the wall. If the egg were thrown at the wall, its initial momentum, well, this would be mass times velocity, right? So let's see, 0.1 kilograms times 15 meters per second. I think that comes out to be 1.5 kilograms times meters per second. What are the final? Well, you could say it's zero right away, but let's do the math. 0.1 kilograms times 0 meters per second. And I think that comes out to be 0 kilograms times meters per second. The final momentum is zero. So what's the change in momentum? Change is always final minus initial. So it's actually negative 1.5 kilograms times meters per second. Therefore, the impulse is also negative 1.5 kilograms times meters per second. And actually, if we throw it at the bed sheet, this all comes out to work out the exact same way. Because what's different? I mean, the initial velocity is no different. The mass is no different. The final velocity is no different. So these actually all come out to be the same. So the change in momentum is p final minus p initial, as is the impulse. So if the impulse is the same in both cases, what's the difference between the two situations? Well, we know that J is equal to negative 1.5 kilograms times meters per second. Okay, so we have to think about the force and the time over which they're acting. So in both of these cases, the impulses are identical, but in the case of the egg thrown at a wall, there is a very large force applied over a small period of time. And in the case of the bed sheet thrown at the sheet, there's a very small force over a big period of time. Okay, so this is small force, big time. This is big force, small time. Now, what would be an example of this? This would be like why we have airbags in cars. If you have an airbag, it stops you over a much bigger period of time than you would stop if you just hit the dashboard. You would hit stop almost instantly if you hit the dashboard. That would be small time, big force. But in the case of the airbag, it's a big time that you're stopping over. Therefore, it's much smaller force. Now, it's not a huge amount of time. It's still relatively small, but compared to the amount of time it would take to stop if you hit the dashboard, it's much bigger. In other cases, if you picture those big, look like bouncy castle things that firefighters put outside of buildings, if the building's on fire for people to jump out of the windows onto, but just really big inflatable things. Well, it stops them. Why doesn't it hurt? Because it stops them over a very long period of time, relatively speaking. Therefore, the force that their body feels is much smaller. So creating a force versus time graph for each one, each graph should have the exact same impulse, therefore the same area. So if the egg is thrown at the wall, there's going to be a very large stopping force over a very small period of time. In the case of the bedsheet, there's going to be a very small stopping force over a very long period of time. Regardless, these both have the same area, same impulse, and also, all right, the same change in momentum. All the same. Just the shape of the graph is a little different. So explain why the egg breaks when thrown at a wall, but not when thrown at a bedsheet. Your answer should include impulse, force, time, and momentum. Well, in both scenarios, they have the same initial and final momentum. Therefore, they have the same change in momentum, the same impulse. But the wall applies a big force over a small time, while the sheet applies a small force over a big time.